Hello student, in this video I am going to talk about a part of the uh, curve representations. How we can represent curves in using graphics devices. Why not simply use a point matrix to represent a curve? Just like a simple plane or simple line or simple polygon, we try to use simple algorithms or metrics or measurements or equations to present the curve. But here in case of curve, there are some storage issues and also limited resolutions. Also it deals with lots of computations and transformations, and also difficult in calculating the intersections or curves and physical properties of objects. Sometimes it becomes more difficult in designing. Suppose we want to control shapes of an existing object. Also might be poor surface finish of manufactured parts. So in those kind of scenario, in those kind of issues, it is not a simple task to represent a curve using point matrix or simple point equations or statistics to represent a curve. So we need to provide some analytical representations for geometric entities so that some parameters can be stored. Designers know the effect of data points on curve, behavior, control, continuity, and curvature. We need to control the pattern of the curve, or we need to control or we need to design the behavior of the curve, or along with that we need to maintain the continuity of the curve and also the curvature so that it becomes perfect one in the displaying devices. Facilitate calculations of intersections, object properties, etc. by using analytical representations. So there are two types of curves we can go through, that is analytic curves or points, lines, arcs, circles, fillets, chamfers, conics. Conics may be ellipses, parabolas, hyperbolas. Those are analytic curves. There are also synthetic curves, include various types of splines like cubic splines, B-spline, beta spline, and Bezier curves. So we will go through this type of objects and how we can represent them in computer graphics in displaying devices. In computer aided design, in many study, in many applications like in mechanical engineering, civil engineering, we try to use or we try to find a math form to represent the curved surfaces so that it looks nice. We can provide smooth contours and it makes it easy to manipulate and manufacture. Also follows a prescribed shape like airfoil design. To study a curved surface, we need to start from curves. So there are various ways to represent the curves. First, we start with a parametric representations. Here, actually, in this whole chapter, we'll go through lots of mathematical equations. What I advise is to what I advise you to just go through and understand it, but we'll try to avoid most of the mathematical explanations during exam also, or but try to understand them for more understanding. But we will try to go more about the concept and theoretical aspects of curve representations, so that we can understand the basic things, basic concepts theoretically, not much with mathematically, but try to go through the flow. So here you can see parametric representations where actually the equation of the line follows with the time. We can represent any functions of curve using parametric equations. Okay, this is a curve, this is a surface. Parametric representation of lines. In case of lines, we have used in Leon-Bersky line clipping algorithm, we use parametric representation of lines. Actually, parametric means when a equations depends upon some parameter, or it might be time in case of representing a line equation. So how is a line equation converted by the CAD or CAM software into the line database? How are the mathematical calculation or equation coded to user commands to generate a line? Here you can see this is P1 at u equal to 0, means that equation of lines depends upon the value of u. So from 0 to 1, that value varies of P. So P equal to P1 plus P equal to any value in the line P will be P1 plus P minus P1. So P1 is this part and this is P2 minus P1 and P2 is this one. Okay, and this distance is P. Okay, so P equal to P1 plus P minus P1, and that part is this one. This is P minus P1 equal to P. Okay, and P minus P1 equal to mu into P2 minus P1. So actually P minus P1 is dependent on this parameter, and P equal to P1 plus mu into P2 minus P1. Here should be mu into P2 minus P1. 0 less than equal to mu, less than equal to 1. Mu should be between 0 and 1. Mu should be between 0 and 1. And P equal to P1 plus mu into P2 minus P1. Here again x, y, z, if it is in 3 dimension, x1 plus mu into x2 minus x1, y equal to y1 plus mu into y2 minus y1, z equal to z1 plus mu into z2 minus z1. That is for xyz value, that is why p equal to p1 plus mu into p2 minus p1 to find the value of p in that line. So actually that is dependent upon the value of mu to store the values of p along the line, and it start from mu start from 0 to 1. And also in case of circles, this is a non-parametric, means this does not depend upon, this equation does not depend upon time or any other variable. Directly x square plus y square equal to 1. So x equal to u, x equal to u suppose. So y equal to 1 minus u square. U is any value of x. So poor and non-uniform definition. So if you follow this non-parametric equation, we will find a poor and non-uniform definition of the line, or the equation of the line, or the presentation of the circle. Square root complicated to the compute. If you try to find a square root in the computation will be more complicated. But if you use parametric, like using the degree, x equal to cos mu, y equal to sin mu. Mu is that distance from that origin to the point. So better definition than A, but still slow. This is third one. Here this is a recursive approach. Okay, this is Pn, we need to find Pn plus 1. So this is original theta, so x for Pn this is xn r cos theta, xn equal to r cos theta, and yn equal to r sin theta as per the polar coordinates. And again xn plus 1 equal to r cos theta plus d theta, r cos theta plus d theta. So it will be like this one. So xn plus 1 equal to xn cos d theta and yn sin d theta. So after expanding this equation, observation is that curves are represented by a series of line segments. So here by increasing a very fraction of the degree, we will get the circle, but this is nothing but a simple straight line, but that value, that portion might be very small. So curves are represented by a series of this type of line segments. Similarly, all conic sections can be also represented like this. This is also a parametric equations where theta is the another variable where we are dependent on. Ellipse. Ellipse is another equation where also we can use same type of parametric equations. Here we can derive the parametric equation of ellipse in the xy plane, which has a center at xc yc and a major and a minor axis as illustrated in the accompanying figure. Their major axis is A, minor axis is B. The ellipse of interest can be obtained by rotating the reference ellipse at the origin by phi about the z-axis and translating it by xc in the x direction and yc in the y direction. If xyz coordinates of the points on the ellipse of the interest are determined or denoted by x star, y star, and z star, and those of reference ellipse are denoted x, y, z, the following equation will hold like this, where this is transformation first xc to yc 0 here from this one to this point or this point to this point. Then we need to rotate the ellipse. That is another way to do, means to use the parametric equation to represent the ellipse. So we can follow this as per the rotation equation or rotation transformations. Same way we can also use parabola using parametric equation to represent in the same way. In the hyperbola also, in the same case, we can use mu. Here mu is the parameter on which it is dependent, equation is dependent to find out the values. So parametric representation of synthetic curve. So here we have used these parabola, hyperbola, or ellipse or circle. These are actually analytic curve. Again we can use same type of parametric equations for synthetic curve also. Analytic curves are usually not sufficient to meet geometric design requirements of mechanical parts. Many products need free-form synthetic curved surfaces. Examples: car bodies, sieve hulls, airplane fuels, wings, propeller blades, shoe insoles, and bottles. There are various examples to understand the various type of curve forms which are free form or might be synthetic curve. The need of synthetic curves in design arises on occasions when a curve is represented by a collection of measured data points and generations. When a curve must change to meet new design requirements, this is generation, this is modification. So in various scenario we might get this type of curves which is synthetic curves, which might be free of form, which might be synthetic curved surfaces, and that might be derived using generation idea or using modification idea. Here you can see the order of continuity is a term usually used to measure the degree of continuous derivatives. This is simplest case linear segment where c equal to 0. Okay, means C0 is less continuous, C1 is high continuous, C2 is most continuous, like that. This is degree of continuous of the derivatives, means the difference of the 2 points. High order polynomial may lead to ripples like this one, high order of polynomial of the equations. Here you can see n is the higher order, but in this equation higher order is 1, so there is no ripples but straight lines. That is why that is less continuous, but this is highly continuous. Splines is another synthetic curve. A mechanical beam with bending deflections or a smooth curve under multiple constraints. Suppose here you can see this is a beam, okay, but it has been bended using this vertical constraints, okay, using some force. So it creates this straight line beam as like a curve. So here these equations are used from the mechanical aspects, mechanical engineering aspects, but try to understand only here this part where we can get the value of the polynomial of the x is 3. So this is cubic spline, means these equations follow a cubic polynomial degree. Drafting, how we can draft the spline? There are various ways. One is Hermite cubic splines, where these are the equation is used, okay. X mu equal to, this is actually coefficients, c3 u cube, c2 u square. So 3 into 4, 12 coefficients to be determined. So in this equation of spline, for any point in the spline curve, we need to find x, y, z using these equations, where these are different polynomials from cube to cube, square, 1 and 0, but c3, c2, c1, c0, those are coefficients. So we need to find 12 coefficients because there are 3 values x, y, z. For any point in the spline you need 3D geometry. So that equation can be converted like this way: mu3, mu2, mu and 1 into this matrix, that gives this one. So here C becomes a factor like or curve like parametric equations. So Hermite cube splines. So here if mu equal to 0, P naught equal to C naught and P naught equal to C, P naught dash equal to C1. So 4 into 3 equation from 2 control points. So here in this equation you can see this is the equation of PU, where I equal to 0 to 3, C3 to we need to find C3 and U3, where mu is 0 to 1. Okay, mu is 0 to 1. That is the parametric equations. So if mu equal to 0, this will be 0. These parts are 0. So P naught equal to C naught. P naught equal to C naught, because everything will be 0, and P dash naught equal to C1 dash C1. So this is P1 P dash, this is P dash. P dash equal to 3 C3 U2, 2 C2 U2 or C1. In that case also it will be only C1, because these are will be 0. If mu equal to 1, if you put 1 in this equation and in this equation, you will find these equations. So our boundary conditions in this case, location of the two endpoints and their slopes of two endpoints of any line. So here P naught in case of U naught, where P naught is C naught, and P naught dash, that is the slope of this line. So that will be C1. Okay. So in that way, in case of mu1, this is P1, and the slope can be calculated using P1 dash. Value is be C1. So in that way, we will go for every point, every value of mu, starting with 0. that is how this equation is converted to this equation, and this equation can be written as this summation equation using the parametric concept. Here mu is the parametric concept, and mu value of mu varies from 0 to 1, and that is why if you vary the value of mu, it can be like this, and you can get the p and p naught dash, that is a straight line. Okay, for any value of mu naught, so any value of mu, so for 0 this will be the line, for mu 1 this will be the line. So but for mu naught starting point is this one, but for another value of mu starting point might be different. So in that way we will get different line segments, and then we need to just complete the line segments. So here C naught equal to P naught, C1 equal to P naught dash, C3 equal to, if we put the values, okay, if we put the values, then we will find this constraints C naught, C1, C2, C3, 12 unknown and 12 equations. So in that case we will get 12 unknowns and 12 equations. Now, but using these parametric equations, all parameter can be determined. So Hermite cubic curve in vector form is this one. So actually you don't need to go more deep on this one, but main fact is that we can find this line, this spline curve, using Hermite cubic spline equations, using parametric value, by putting the values of mu's in the equations. So actually that is main part of this video. I will explain more about next Bezier curve. We don't need to go more deep about this mathematical explanation. Just understand what is Hermite cubic splines. Try to understand a bit about this equation, and how can we use, or how can we derive this equation or use this equation to draw this spline curve. That's it on this part. If you have any doubt or any confusion, please let me know. We'll try to resolve it over Google Meet, and you might obviously have some doubts because this is a bit tough. And also by that way, if you let me know, I will also try to understand that way I can also learn. So that's it. Thank you.